All right, we've got lots to look at in Chapter 8. We start talking in this chapter about quantities within chemical reactions, and we're going to look at the idea of stoichiometry within balanced equations. We'll start with sections 8.1 to 8.4, where they talk a little bit, some background information, just relating it to our environment with climate change, talking about carbon dioxide in the atmosphere, and then we use recipe, making pancakes, to talk about the relationships between ingredients. We will then carry that over to molecules with mole-to-mole conversions, and then mass-to-mass conversions. All right, so starting out with climate change, the idea of too much carbon dioxide. Now, there are a lot of things that contribute to global warming, but carbon dioxide is the one that we have focused on, that scientists have focused on as being a primary target, not because carbon dioxide is the most horrible molecule for producing climate change, but because there's just so much of it, because of human actions. So, for example, when you combust fossil fuel, such as octane, that is what makes up gasoline, or the majority, it's not the only thing in gasoline, but it's sort of our standard molecule for gasoline. When we combust that, we looked at combustion reactions, and we said that combustion reactions, if they're efficient, produce water and carbon dioxide as their two products. Those are the only two products of a combustion. Carbon dioxide then is a greenhouse gas. It's believed to be not wholly responsible, but a majority of what's responsible for global warming, because there are so many of us driving cars. There are so many industries that are burning fossil fuels, that are combusting these things that produce carbon dioxide. So why, what's the mechanism behind this? Well, the reason the carbon dioxide is a problem is because it is what we call a greenhouse gas. Now, if you've ever been in a greenhouse, you know the idea is that it's made up of glass or plastic, something that allows light, visible light energy, to come in, but then once the energy is inside, it doesn't escape as easily. It's lost some of its energy coming through that glass or that plastic, and it's unable to then exit the same way it came in because of that loss of energy. Same thing with our atmosphere. Our atmosphere acts like the glass or the plastic on a greenhouse. Energy comes in from the sun, but then there's a little bit of loss of energy because of interactions with the atmosphere, the molecules in the atmosphere, interaction with the surface of the earth. It's coming in. Okay, so light comes in here, gets absorbed slightly, loses some energy, and then it is converted to heat energy. Okay, and then that heat energy tries to go out, and normally some of it would radiate back out to the atmosphere, and some of it would stay here. Okay, we don't want it all to escape, because that's what makes Earth habitable for us, is that we, do have a particular temperature that works for us. But with carbon dioxide, it adds like an extra layer of that glass. So there's this insulation layer now that even more of the heat is being trapped and focused back to Earth. Okay, so carbon dioxide, other molecules such as methane. Methane is a huge producer of that. A lot of sulfur compounds and some nitrogen-containing compounds will do this as well. There are a lot of molecules, but carbon dioxide outweighs them all enormously. So when we say it outweighs it enormously, we won't look at the other reactions, but let's just look at a reaction in which carbon dioxide is being produced. How much is being produced? Well, if we look at the combustion of octane, which is C8H18, and one of the components of gasoline, okay, here is our balanced equation for that combustion. So for every 2 moles of octane, okay, we're using up 25 moles of oxygen, and we're producing 16 moles of carbon dioxide, 18 moles of water vapor. Okay, so it's 2 to 16 here. So for every 1 octane, we're producing 8 times the number of moles of carbon dioxide. There's a lot of carbon dioxide being produced here. And if you look at other hydrocarbons that are being burned, some of them are even larger than C8H18, which in turn is going to produce even more CO2. So it becomes an issue. It just starts to build up. Okay, so as we said, chemical equation, 16 moles for every 2 moles of octane. Now, we know approximately how much fossil fuel the world uses in a year. So using that, we can estimate the world's annual CO2 production using that balanced chemical equation. Now, we're not going to go through that calculation, but if you carry out that calculation, it shows that our annual carbon dioxide production, just from combustion of fossil fuels, matches the measured annual atmospheric carbon dioxide increase. So there's a correlation there. If you map the amount of CO2 that's increasing, you map fossil fuel combustion, they track with one another. So again, correlation doesn't necessarily imply causation, but there's a strong implication here that fossil fuel is tied to the increase in CO2 production. Now, there is a plot in your book on page 250 that shows that correlation. So you can look at that and you can kind of make a decision for yourself. But what we want to look at, the reason we're talking about that is we want to look at that idea of how do we use that balanced equation to determine that production of CO2 in a year. How did we get from the amount of fossil fuel we consume to the amount of CO2 being produced? And we're going to look at it just in terms of stoichiometry. Stoichiometry is the numerical relationship between chemical quantities in a balanced chemical equation. So in other words, this is where we're going to focus on the coefficients that are in that balanced equation. Now remember that if we have a balanced equation, that allows us to predict the amount of products that form in a chemical reaction based on the amount of reactants. Again, that's tied to the coefficients. That's the number of moles of reactant or product that we have within that reaction. So if we can predict the amount of product that we're going to form, we can also predict if we want to form a certain amount of product. I need to make this many moles of this product, then I can use that to calculate the amount of reactant I need in order to form that much. That's what we're going to focus on in this chapter. Okay, those relationships of the coefficients in balanced chemical equations. Okay, so, sorry, I get ahead of myself on these. So we're going to predict how much of one reactant we need to completely react with another reactant and produce a certain amount of product. Now, you'll see that I love food analogies. We already talked in class about pizza. We looked a little bit at relationships with pizza. Well, now we want to look at another recipe. We're going to use the example of making pancakes. So our recipe for making pancakes is a cup of flour, 2 eggs, half a teaspoon of baking powder, and then when I mix those together, I end up with 5 pancakes. Now, there's probably some other stuff in there, but those are the key ingredients. We want to look at those relationships. A cup of flour, 2 eggs, half a teaspoon of baking powder will yield 5 of these pancakes that I'm going to make. All right, so let's keep that in mind. So we have this numerical relationship. I need 2 eggs if I'm going to make 5 pancakes, for example. So if I have 2 eggs and I have, at least enough of the flour and the baking powder, then I can make 5 pancakes. Now I can write that as a ratio, 2 eggs to 5 pancakes, which then gives me conversion factors. Anytime I can write a ratio, remember, I have a conversion factor. All right, well, let's say that I need at least 2 eggs to make these 5 pancakes. What if I have more eggs than that? What if I have 8 eggs? So, and again, let's assume I have plenty of flour, plenty of baking powder, but I have 8 eggs, and I need to see how many pancakes I can make. I've got a crowd coming over. Okay, you've probably already done this in your head while I'm talking. You take those 8 eggs and then you multiply it by that ratio of 5 pancakes to 2 eggs, and I see that I can make 20 pancakes if I have 8 eggs and enough of everything else. Okay, so my 8 eggs limits me to 20 pancakes. That's quite a few pancakes. All right, it's the same thing when I look at mole-to-mole conversions within a balanced chemical equation. So the balanced chemical equation is my recipe for how I'm going to mix everything together and make my final product. All right, now in this recipe, or this balanced equation, we're going to combine 3 moles of hydrogen with 1 mole of nitrogen, and those are going to produce 2 moles of ammonia. So if you look at the image up here, you can see how that breaks down. So the nitrogen is one of those diatomics. There are 2 individual nitrogen atoms, so that bond breaks apart. The hydrogen is also a diatomic. Those are bound together. Each one of those hydrogen diatomic molecules breaks apart and produces 2 individual hydrogen atoms, so a total of 6 hydrogen atoms. And then they recombine in a ratio of 3 hydrogen atoms to 1 nitrogen atom. So I can do 2 of those. All right, so here's what we're going to make. There's our balanced equation. Let's just keep that here. All right, so I need 3 hydrogen molecules to react with 1 nitrogen molecule to form 2 ammonia molecules. That's the ideal case. Every one of those then can be expressed as a relationship of a ratio. 3 hydrogens to 1 nitrogen to 2 ammonias. Now, since we don't normally deal with just individual molecules, you can express it as molecules, but what we want to do is express that ratio in terms of moles, because remember, moles is our universal translator. If I know the number of moles of something, and I have a periodic table that shows me the relationship of grams and moles, then I can go from number of moles, numbers of things that I need, to the mass that I need to weigh out. All right, so that's the key relationship. All right, so here's a problem. We're told that we have 3 moles of nitrogen. Okay, so we get 3 moles of this, and I've got plenty of hydrogen, more than enough, as much as I need. So that's like my 8 eggs. I have 3 moles of nitrogen. How much ammonia can I make? So I have to start with what I'm given, 3 moles of nitrogen. Okay. Now I want to get rid of moles of nitrogen, and I want to be left with moles of ammonia. Okay, now if I look at this, remember, as long as it's the same mole to mole, and I'm changing the species. If I want to go from one chemical species to another, I can do it in terms of moles. I can't do it in terms of anything else. I couldn't say grams of ammonia over grams of nitrogen. I guess I could say molecules, but we don't want to work with molecules. We're going to work with moles. So how do I know the relationship of moles of ammonia to moles of nitrogen? Well, that was up here in our handy-dandy balanced equation. So 2 moles of ammonia and 1 mole of nitrogen. Moles of nitrogen cancel out. That tells me that I can make 6 moles of ammonia. Okay? Now, so I'm overwriting this. Sorry, I tend to get ahead of myself on these things, but bear with me. So if you look at your plan to get from moles of nitrogen to moles of ammonia, you need that relationship of 2 to 1. And then just a little bit cleaner version of that you can see. 3 moles of nitrogen times the 2 to 1. Okay, that's pretty simple. Now, let's look at another example of this. What if we don't have enough oxygen when we're burning our octane? The balanced equation shows that there are 2 moles of octane required for, or if we have 2 moles of octane, we require 25 moles of oxygen in order to completely combust that reaction. Now, if you don't have enough oxygen, other things happen. You do get other products, but we're not going to go into that. We're just going to assume that, we may not have enough. So with octane, if I don't have enough oxygen, what's going to happen is I'm going to start building up stuff like carbon monoxide or ozone, which is O3, things that are pollutants, are not good. We know carbon monoxide is toxic to us as humans. Ozone actually is too. Again, ozone is one of those things we want in the upper atmosphere, out in the stratosphere. We don't want it on the surface of the Earth. We don't want to be breathing these things. So a shortage of oxygen in a combustion is actually a very bad thing. Okay? So there have been amendments to what is known as the Clean Air Act, and in particular in 1990, there was an amendment to the Clean Air Act that required oil companies to put additives in gasoline to make sure there was enough oxygen in there in order to completely combust the gasoline and get the carbon dioxide. Okay, because while carbon dioxide is a greenhouse gas, that's a longer term problem. It wasn't seen to be as much of a problem over the last 20 to 100 years or so. The immediate problem was that we were poisoning ourselves with these pollutants from incomplete combustion. So those additives actually, they do decrease your fuel efficiency a little because you're adding mass to it that actually is not burnable. It's not a fuel, you're adding oxygen, but the trade-off is that you're not poisoning yourself with that. But this is what they did. They used this balanced equation to determine if I have this many molecules of octane or whatever else in a typical gallon of gasoline, how much oxygen do I need to have? So they could carry out the calculation and say, okay, I need at least this many moles of oxygen in there. I have this many moles already. How many more do I need to put in order to completely combust that stuff? Now, what was the additive that they added? How did they put oxygen in there? Well, if you think about it, you can't really put pure oxygen into gasoline. Bad idea. It's not going to stay in there, and oxygen's highly flammable, so you don't want free oxygen floating around in your gas tank. But you need a compound that has some oxygen in it. Well, the one thing that was chosen by the oil companies as their best bet was something known as methyl tertiary butyl ether, or MTBE. And you can see the formula right here. So it's still a hydrocarbon, carbon, hydrogen, those are combustible, those kind of act as fuel, and then it's got this little oxygen right here in the middle of it that can provide some oxygen to this reaction. Now, it provided the oxygen, it helped with the combustion, but there were some, of course, side effects from this. MTBE does not break down readily in the atmosphere. And so if it didn't get into the combustion, or if somebody spilled some gasoline or something like that, that MTBE, along with the gasoline, made its way into drinking water supplies through gas stations, boat motors, anything, where there was a fuel leak. So they had to back off on the use of MTBE and find something else. So the choice now is actually ethanol. Now, ethanol has been touted as the fuel of the future. We're going to make ethanol from corn, and we're going to put that in our gas tanks and drive. That's never going to be really feasible just because of the energy output from ethanol versus what it takes to make ethanol. But we still have it in our gasoline. When you go to the gas pump, you're going to see ethanol in your gasoline. Why is that? Well, that is the substitute for the MTBE. That is what increases the oxygen content and gives you cleaner combustion. That was the whole point of the ethanol, or it is now. The whole point of the ethanol is to give cleaner combustion. Ethanol wasn't originally used because it was more expensive than the MTBE, but since the MTBE became an environmental hazard, it became regulated, and that drives up the price. It makes it now economically feasible to use the ethanol. All right, just a little side note on that one. All right, so mole-to-mole conversions within a balanced equation, pretty easy. You just throw in the coefficients, there you go. Well, we don't use moles, we use mass. We want to measure something out. I don't want to end up with 8 moles of aspirin. I want to end up with 320 milligrams of aspirin. I want something I can measure out and a dose that I can take, or I want to, know how many pancakes I'm going to make, that sort of thing. So maybe I'm doing my pancakes by mass. So mass-to-mass conversions are going to be the ones that you see most often. These are the ones you really need to become proficient in because you'll be going back and forth with these all the time. So the chemical equation has our conversion factors in terms of mole to mole, but we want to know mass to mass. So here's the outline. Here's what we're going to do. We want to know the mass of product B. So I need to know how much reactant A. If I start with a mass of reactant A, I've got 5 grams of A. Then if I know the molar mass of that, I know what A is, it's some element or compound, I calculate molar mass, that allows me to convert to the number of moles of A. That's the only way then I can switch from one species to the other. I'm going to change from moles of A to moles of B by using the ratio from the balanced equation. Okay, so I need a periodic table and I need a balanced equation in order to do this. I use the ratio to convert to moles of B. Now I calculate the molar mass of B and use that to get myself back to mass of B that I'm looking for. Okay, so remember this layout, mass to moles to moles to mass. Don't do what I did and take about 3 years to learn this. I actually didn't quite figure this out, I'm a little embarrassed to say, until I became a stockroom worker, started working in a stockroom having to prep solutions for different labs, for people who were teaching labs. And that's when it really clicked what I was trying to do here. I was trying to get a particular amount of a product or a particular concentration of a solution, and I had to walk through this process over and over and over again, and it started making sense after that. So do as I say, not as I do. Go ahead and learn this now and save yourself 3 years trouble. So of course we want to look at an example of this, and let's go back to our combustion. So we've got our octane being combusted with oxygen. We need 25 moles of that oxygen to completely combust it. What mass of carbon dioxide? So what we're looking for is mass is grams. So how many grams of CO2 is being emitted by an automobile for every 5 times 10 to the 2 grams, which is, if you work that out, 500 grams of pure octane being used. Okay, so what we have here, 500 grams of octane. All right, so we've got the balanced chemical equation. That's giving us the relationship between the moles of octane and the moles of carbon dioxide. But we don't have moles of octane, so we've got to first get from grams to moles. Sorry, going the wrong way there. There we go. All right, so here's our map. We've got to start with that 500 grams. Okay, and then we're going to use the molar mass of octane. We're going to get number of moles. Then we're going to use our ratio. Okay, so if we look here in the balanced equation, there are 2 moles of this, and there are, oops, sorry, looking at the wrong thing, 16 moles of this. Okay, so we've got that relationship, and then we'll take the molar mass of the carbon dioxide to get us to grams of CO2. Okay. So here are those relationships we're going to need all along. You can calculate these out, but here's the molar mass of octane, 114.3 grams in 1 mole. Now notice they've already flipped it around the way you need it because you need grams to cancel out. Here's the 16:2 ratio here to get from octane to carbon dioxide, and molar mass of CO2, which is 44.01. All right, so we've got all of our numbers, we've got our plan. All we got to do is put in our mathematical operators, and away we go. Okay, so we had the 500 grams of C8H18, and hopefully you can write smaller than I can, or you're going to be using lots of lines in your paper. 1 mole C8H18 to 114.3 grams, and I'm going to leave the species off that one. 16 moles to 2 moles of CO2 to C8H18. Okay, so the grams have canceled out. Now moles are gone, so now I have moles of CO2, and then the 44.01 grams of CO2 per 1 mole. Moles cancel out. So 500 times 16 times 44.01, divide by 114.3, divide by 2, and you end up with 1.5 times 10 to the third, or 1,500 grams of CO2. Okay. So you can see mass-wise, again, if you looked at mole-wise, it was 8 times more CO2. Mass-wise, in this case, it's 3 times as much mass. But then again, we're not worried so much about mass when we look at CO2. It is the number of moles that we have in there. Because if you look at the molar masses, the octane is much more massive than the CO2. So if you think about it in those terms, it makes sense that it would only be 3 times the mass of CO2 because it's a lighter molecule. It's 8 times the number of moles, but only 3 times the mass. Okay, so it's good to kind of stop and look at your answers and think about, do these make sense? Do they match with what you know? But that's a lot of carbon dioxide. So that is mole-to-mole, mass-to-mass relationships within a balanced equation, so basics of stoichiometry. In the next 2 sections, 8.5 and 8.6, we're going to look at some more pancakes. We're going to talk about the idea of a limiting reactant, a theoretical yield, and a percent yield, and then we will look at examples of finding those based on initial masses of reactants. These are, again, very important reactions to know because this is usually what you're trying to do. You're trying to figure out how much of something can I make from these starter ingredients.